Well, so today we will be continuing our talk on compressible flows. I had in the last class what I did was I had covered, or rather I had identified what is compressible flow, why Mach number is important, and we had also defined the stagnation properties and the sonic properties, isn't it. So, next what I had planned to do is just to show you the effect of area change on compressible flows, okay? Because normally we have seen that for incompressible cases we have seen that an area change, it suppose there is a contraction, it accelerates the flow, when there is an expansion it is vice versa. So, in this particular change, apart from velocity, the certain other changes are expected. So, let us see what are the changes. We will be starting from the basic equation of the energy equation, the final form that we had derived in the last class, the final form which we had derived, from where we had got that the enthalpy head and the kinetic energy head remains constant for an adiabatic isentropic situation. So, from there we will start and we will see how area changes affect the compressible flow cases. Okay. Now, the thing is, it is changes in area on the area change, actually what it does, it changes the velocity and it changes the pressure as well. Now, let us start from the basic equation which we had derived in the last class, dp plus rho dp by rho plus u du equals to 0, or in other words we can write it down as dp equals to minus rho u du, isn't it. Now, dividing both sides by rho u square, what we get? We get dp by rho u square, this is equal to minus du by u. Okay. Now, this is one equation. Now, from continuity, equation of continuity, what do we get? From equation of continuity we get we all of us know W equals to rho A u. Now, if we take the logarithmic differentiation, like taking log and then differentiating, which we had already done in the last class I believe. So, logarithmic differentiation, what does it give? It gives us an expression something of, I hope you have noted this down, it gives us dA by A plus d rho by rho plus du by u, this is equal to 0, or in other words dA by A, this is nothing but d rho by rho, sorry, minus du by u. Okay. Now, from here what we had got? We had obtained an expression for du by u or minus du by u. So, we can substitute this particular du by u with dp by rho u square, isn't it. So, if we do it, then in that case what do we get? We get this as d rho by rho plus dp by rho u square, right, or in other words it can be written down as, this can be written down as dp by rho u square 1 plus u square by dp d rho. Can we write it down in this particular form? We can write it down in this particular form, and what is this particular term equals to? dp d rho, this is A, the rather it is A square, isn't it. So, the velocity, the acoustic velocity in that particular medium under that particular conditions. No, not minus d rho by rho, it is sorry, very sorry, correct. Actually, here only I had made a mistake, here it is minus d rho by rho, here only I had made a mistake, that is why it came in that way. So, this is the situation. So, therefore, this can then be written down as dP by rho u square. This is nothing but equal to 1 minus m a square, is not it? So, therefore, we find out that how pressure will change with area, that depends upon the Mach number, is not it? So, we find that if this Mach number is less than 1, then a positive area change will give rise to a positive pressure or a pressure increase. A negative area change will give rise to a negative pressure. Okay? And similarly, if a Mach number is greater than 1, just the reverse takes place. Is this part clear to you, that for Mach number less than 1, what we have, an area change causes a pressure change of the same sign, and for Mach number greater than 1, an area change causes pressure change of the opposite sign. Agreed? Achha. Now, let us see how area change affects velocity change. Now, here I had already reduced a equation between dP by rho u square and du by u. Yes. So, therefore, this particular relationship, instead of dP by rho u square, I can write it down as minus du by u. Okay. So, if I substitute it, then what do I get? I get the expression as dA by A equals to minus du by u into 1 minus m a square. So, from this what do I get? I see the area change has an opposite effect on velocity change, depending upon whether Mach number is greater than 1 or less than 1. If it is less than 1, an area change, maybe the positive area change causes a negative velocity change, or in other words, when there is an expansion, we have deceleration or we have a velocity decrease, and when there is a contraction, velocity or the flow, it accelerates. This is in agreement with what we have observed for incompressible cases. But when Mach number is greater than 1, the reverse situation happens, is not it? We find that for this particular case, for Mach number less than 1, area change causes a change of velocity of opposite sign. Positive dA means negative du for Mach number less than 1, and for Mach number greater than 1, an area change causes a velocity change of the same sign. So, therefore, from this what do we deduce? We deduce that for the subsonic range, if Mach number is less than 1, then in that case what happens? The nozzle will be something of this sort. Flow occurs in this particular direction. For this particular case, we know dP less than 0 and du greater than 0, is not it? And what about a diffuser? A diffuser will be something of this sort. So, this is a nozzle and this is a diffuser. Again the flow is in this particular direction. In this particular case, we get dP greater than 0, du less than 0, dA greater than 0. Agreed? So, therefore, a nozzle it is a convergent profile, a diffuser is a divergent profile. This accelerates flow, this decelerates flow, just the same way as we had studied for your incompressible cases. Agreed? But we find that when we go for the supersonic nozzle, in this particular case, we find that the nozzle will be something of this sort. Here MA is greater than 1, flow occurs in this particular direction, and we find that for this particular case dP is greater than 0, du is less than 0. So, therefore, we find that for this particular case the supersonic nozzle is of this particular form and the supersonic diffuser has a convergent profile. Again the same thing, flow is in this particular direction. Okay. So, from these things what do we deduce? We deduce the important observations are that at subsonic speed, that means when Mach number is less than 1, these cases a decrease in area increases speed of flow. A subsonic nozzle therefore, it should have a convergent profile, a subsonic diffuser should have a divergent profile, is not it? So, we can deduce it or we can just jot it down in this particular fashion. At subsonic nozzle convergent profile, just I am writing down whatever I have drawn and shown you. Subsonic diffuser divergent profile. On the other hand, if we take a supersonic nozzle, that means for Mach number greater than 1, we find that the effect is just opposite. We find that supersonic nozzle, it has a divergent profile and a supersonic diffuser, it has a convergent profile. And this particular thing, this supersonic, the divergent nozzle to produce supersonic flow, that is very frequently it is used in missiles and launch vehicles. In aerospace we use, we as chemical or mechanical engineers, we do not come across this particular situation. Okay. So, this is something very important that you should be noting, that whenever we are the behavior of compressible flows, they are not consistent over the entire range of Mach number. One type of flow characteristics are exhibited for Mach number less than 1 or under subsonic conditions, just the reverse type of phenomena is observed for supersonic conditions. And that explains why this particular fact, Mach number equal to 1, is so very important. And for Mach number equal to 1, this is usually it is termed as choked flow condition, or the condition of choking is when Mach number equal to 1. Now, let us see that when we have a flow through a convergent nozzle, okay, for that particular case, let us see what is the maximum flow rate, when we get the maximum flow rate, and so on and so forth. So, before that I would like to show one more thing to you. I had expected this particular question from you. Let us see, in this particular case what do we find? We find that for subsonic cases what do we get? We suppose we start from a very low velocity, okay, and we keep on increasing the velocity. The profile is convergent. What happens? Gradually with increase in velocity, the Mach number keeps on increasing till it reaches Mach number equal to 1. If we keep on increasing the Mach number further, we cannot do it in this particular case. We can just come till Mach number equal to 1. We cannot accelerate the flow further under these particular circumstances. Is it clear to you? So, therefore, if we want to, suppose we want to start, or we have started with a very low velocity, okay, and from that particular velocity we would like to accelerate the flow to subsonic conditions. That means, we would like to go from Mach number less than 1 to Mach number greater than 1. Can we do it by either a subsonic nozzle or a supersonic nozzle? Can we do it? We cannot do it. So, therefore, for that particular case, what do we need if we start from a very low velocity and we have to go to the supersonic range? We have to use a convergent divergent nozzle, otherwise it is not possible. So, for that particular case what we need is, it is something of, we have to do something of this sort. Suppose if we want to obtain supersonic stream starting from very low speeds at the inlet. So, here it is say Mach number, it is almost equal to 0, flow occurs in this particular direction, this is known as the throat. Now, as we keep on increasing the velocity, we find we come to m a equals to 1 here, and then in this divergence section we get m a greater than 1. So, therefore, we find that in order to accelerate flows from the subsonic to the supersonic range, what we need is we need a convergent divergent profile of a nozzle. It has to converge in the subsonic portion, it has to diverge in the supersonic portion. Such type of nozzles are known as convergent divergent nozzle, or it is also known as the de-Laval nozzle, named after the person who had first used it and designed it. So, therefore, there are certain things that we can note. If we take up the expression relating dA by A with this, what do we find? We find that Mach number can be equal to 1 only when Mach number can be equal to 1 only when dA equals to 0, or in other words, where is dA equals to 0? At the throat, at that particular portion where the area does not change any further. Okay. So, therefore, certain observations we get from this particular equation. The observations are firstly that, okay, I will write it in a separate page, that I will write down the equation once more, that will be easier. From this equation we get, from this particular equation we get that Mach number can be equal to 1 only for dA equal to 0 or at the throat. It cannot be equal to 1 under any other condition. Agreed with me? Again the same thing. Does it imply that Mach number is always equal to 1 at the throat? Because dA equals to 0 can be obtained either by m a equals to 1 or du equal to 0. So, therefore, Mach number might not be equal to 1 at the throat, but for that condition du equals to 0, or fluid at the throat has to be at rest or in uniform motion, it cannot accelerate at the throat. Do you get my this point? This point is extremely important. First thing we get is that if we want choked flow condition, if we want m a equals to 1, that can only happen only at the throat where dA equal to 0. We cannot have Mach number equal to 1 under any other condition, number 1. Number 2, that does not imply that Mach number has to be equal to 1 at the throat, or in other words, flow has to be under choked flow conditions at the throat. We can have a nozzle or a converging diverging nozzle also, where the flow throughout is subsonic. That means, Mach number is less than 1 at the converging section, it continues to be 1 at the diverging section, it never becomes equal to 1. We can have a condition where Mach number is greater than 1 throughout the entire region. Okay? We can have that. It is not that Mach number has to be equal to 1 at the throat, but if we are not having choked flow conditions at the throat, then the fluid either has to come to rest or it has to be under uniform motion at the throat, or in other words, if m a not equal to 1, then du equals to 0 at the throat. Clear to all of you? So, therefore, this is the thing which you have to keep in mind, that for this particular case, if we got to have Mach number equal to 1, it can be under this particular condition. but we can also have situations where we find that the flow throughout is here, it is Mach number less than 1, flow occurs, in this case also Mach number is less than 1, or in other words, if we plot Mach number with distance, say this is Mach number equal to this is 1. So, we can always have something of this sort. It starts in this way, it ends, but always it is subsonic throughout. Okay. We can also have a situation maybe where Mach number is greater than 1 throughout the case, or in other words, we can have a situation where it is something of that sort. It never comes, the flow is supersonic throughout, and in this particular case it is subsonic throughout. We can also have these two conditions, but we need to remember that for this to occur, du has to be equal to 0 under this particular condition. In this particular case, du has to be equal to 0. This is the thing that you have to remember. So, these are the two cases where Mach number is not equal to 1 at the throat, but yet the flow can occur, because the fluid at the throat is either at rest or in uniform motion at the throat. So, this is very clear that if you want to accelerate the flow from supersonic to from subsonic to supersonic conditions, you cannot do it for a convergent nozzle. We have to go for a convergent divergent profile, where the Mach number has to be equal to 1, or the choked flow conditions can be approached only at the throat. Okay. Now, let us see what about the flow rates and what about the flow under choked flow conditions. Okay. So, let us, we are going to do say isentropic flow . So, for this particular case, we know that for an ideal gas in a converging nozzle, for an ideal gas in a converging nozzle, what do we know? W equals to this, all of us know, or in other words, W by A, this is nothing but G, this is equal to rho u, this also, this we know. Now, since assuming, we have already assumed it to be an ideal gas, so therefore, this rho can be written as P by R T, yes or no? This U can be written down as A into M A, agreed. This A can be written down as root gamma R T, we can do whatever we are doing. Okay. So, therefore, into M A of course. So, therefore, after this we can just rearrange and we can write P by P 0 into P 0. We can do this, yes or no? Root over of T 0 by T root 1 by T 0, fine, root gamma by R into M A. Can this be done? I have just introduced the stagnation properties. Why? Because I know P by P 0 in terms of T 0 by T 0, and I can easily substitute them. Okay. So, that I can, my target is to express this particular mass flux or the mass velocity in terms of certain easily measurable parameters, and to find out on what this flow rate depends. If I can know on what the flow rate in a converging nozzle depends, or on what parameters the flow rate depends, then I know how to manipulate those particular parameters and control, increase or decrease my flow rate as I desire. Okay. So, therefore, I would like to find out on which measurable parameters my flow rate depends. Just for that, I would like to express this expression in terms of certain known input or certain measurable parameters, right. So, therefore, After this what I can do, I can just substitute P by P0 in terms of T0 by T. I think in the last class I had defined those particular terms. P0 by P equals to this particular term, isn't it? And I had also defined T0 by T. I have that also, thank God. Here also I had defined T0 by T, isn't it? So, instead of T0 by T I can substitute this, instead of P0 by P I can substitute this. Okay. Just let us do these two substitutions and then let us find what do we get. We get W by A, this is equal to, in that particular case, T0 by T. Instead of P0 by P I am writing gamma by gamma minus 1, okay, and T0 by T whole to the power half P0 by root over T0 root gamma by R into Ma, okay, and then I can write this as T0 by T whole to the power minus of gamma plus 1 by 2 into gamma minus 1. Okay. I have combined these two terms, okay, and then it comes as P0 Ma by root T0 root over of gamma by R, or if I arrange it slightly more, it is almost the same thing, rearranging and writing. I am just bringing all my known parameters to the towards the left. This whole thing T0 by T I will substitute, I get 1 by 1 plus gamma minus 1 by 2 Ma square, this is gamma plus 1 by 2 into gamma minus 1. So, this is the final expression. Now, in this particular case W by A equals to. So, in this particular case what do I find? I find gamma R P0 Ma T0, all these parameters they are constants. Okay. What is the only variable in this particular equation which can vary my mass flow rate or mass flux? The only variable is P0 Ma gamma R T0 constant. So, the only thing which influences W is Mach number. So, gradually I would like to show you the importance of Mach number and why Mach number equal to 1 is so very important and why Mach number is so very important. That is what I would like to show you. Okay. So, therefore, we know W by A, this is a function of Mach number only, it does not depend on anything. Okay. So, therefore, by varying Mach number we can vary this, and under what condition will we get a maximum of W by A, or under what condition do we expect to get W by A max? This will depend definitely only on the Mach number, okay, and the condition which will give you W by A max can be obtained as d of dma equals to 0, yes or no. From this particular condition I can find out, I can get an estimate of W max, isn't it. Now, let us differentiate and let us find what is this expression. So, what basically you are required to do, this whole thing can be taken as a constant k. You need to perform, one Ma is there. So, you need to simply very sorry, P0 gamma R T0, very sorry. So, you need to perform this particular differentiation. So, you can take this portion as say K1 a constant, and here also this particular portion can be taken as K2. So, therefore, Mach number is the only variable and you can perform the differentiation. And on differentiating, what do we get? We find that if we differentiate it, the expression reduces to 1 minus Ma square. You just perform it in your hostels and then you see whether you are getting it yourself or not. This equal to 0, isn't it? This is the thing which we get, or in other words we get just on substitution Ma square into gamma plus 1 equals to 2 plus gamma minus 1 into Ma square, and if you solve it, what do you get? We get from this particular condition ma square equal to 1. So, therefore, we were talking about the choked flow conditions, or rather we were talking about the we will dA equals to 0, when dA equals to 0, ma equals to 1 and so on and so forth, and we find why is ma equal to 1 so very important, because that gives us the maximum flow rate from the converging nozzle under the present circumstances. Okay. So, therefore, we find that for Mach number equal to 1, we get the maximum flow rate under the present circumstances. The discharge is maximum. Okay. Now, let us see that where do we get? We have already seen that we get Mach number equal to 1 where dA equals to 0. Okay. So, just a little more substitution if we do, then in that case we get, we know u equals to A into ma, we know this. Okay. Now, again if we or this can be written down as root over of gamma r t into ma, fine. Now, again if we perform that we take the log of both sides and we perform the logarithmic differentiation. So, by performing this logarithmic differentiation, what do we get? We get du by u equals to dma by ma plus half dt by t, isn't it? And from the previous expressions where we had obtained t by t 0 by t, from this particular expression also we can perform the logarithmic differentiation. Okay. So, that we get two expressions of dt by t and we can equate them. So, that particular expression 1 plus gamma minus 1 by 2 ma square whole to the power minus 1, isn't it? So, in this particular case we get dt by t, this is equal to minus gamma minus 1 ma square by 1 plus 1 by 2 ma square dma by ma. Okay. So, now what we can do, instead of this dt by t, we can substitute this particular expression, yes or no? Just do it and see what we are getting. If we do it, we find that du by u, this becomes dma by ma 1 minus gamma minus 1 by 2 ma square by 1 plus gamma minus 1 by 2 ma square, or this can be written down as 1 by 1 plus gamma minus 1 by 2 ma square. This is the thing that we can get from this particular condition. So, therefore, we find dA by A if we write, then in that particular case we have already got du by u in this from here. Okay. We already had a equation of relating du by u and dma, just a minute, we had one particular equation, yeah. We had dA by A equals to this. Okay. So, in place of du by u, we can substitute this particular equation. Okay. And then we get, this is ma square minus 1 by 1 plus gamma minus 1 ma square by 2 dma by ma. So, therefore, we had obtained that we get the maximum flow rate for ma equals to 1, and for ma equals to 1, dA equals to 0 or A has to be equals to constant, or in other words we observe that this happens only at throat and nowhere else. Okay. So, this means m a equals to 1. As I had told you, this happens only at throat and nowhere else, and discharge maximum at m a equals to 1. So, therefore, we find that properties at the throat can be the critical properties, and when properties at throat critical properties, nozzle is said to be choked. It delivers the maximum flow rate. This portion is clear to you. Okay. So, we find that for m a equals to 1, that happens only at the throat and nowhere else. Under this particular condition, the discharge is maximum, and under these conditions the nozzle is said to be under choked flow conditions. Agreed? So, this shows why m a equals to 1 is so very important for all our purposes. Now, let us see one more thing. Let us see that suppose from a very large reservoir, say the flow has initiated in a nozzle, okay, and this is connected to a container which has a valve. Okay. Now, since the flow has initiated from say a tank and flow is occurring under isentropic conditions. So, what do we know? Conditions at the tank are the stagnation conditions, right. So, here the properties are P 0, T 0, rho 0, etc. Okay. Here just at the exit of the nozzle, P exit or P E, and in this particular tank we have a back pressure which is P B. This back pressure is regulated by means of opening or closing this particular valve. Okay. So, P E is the pressure at the exit plane of the nozzle. If I write it down, P B, it is the back pressure varied by valve. Now, let us see what happens. So, initially what we can do, we can gradually, initially this valve is closed and the entire system is at a constant pressure, no flow occurs under that condition, right. So, if we plot say P by P 0 as a function of distance across the nozzle, distance along nozzle, and along with this pressure we would also like to plot the flow rate, which is W by A. Usually we take the entire that constant thing which was there, this is as a function of. So, initially what do we find? Initially we find that everything is equal and therefore, the curve is something of this sort, where this is P 0 equals to P E equals to P E. Under that condition there is no flow. Then what we do? We gradually try to open this particular valve. As we open this valve, P B reduces, is not it? P B and P E are equal. Okay. So, therefore, when P B reduces, P E also reduces, and gradually P E becomes less than P 0, right. P E becomes less than P 0, and when this happens, due to this pressure, some flow starts occurring. Okay. So, gradually if we keep on opening, this is for 1.0 and P equals to P 0. Now, when this happens, we get something of this particular case, okay, where gradually we are reducing it, and here in this case P e equals to P b and this is less than P 0. Agreed? And gradually we find that the flow starts. Fine. We keep on continuing this, we find that we get reduced and reduced pressures here by keep on opening the valve. P b becomes equal to P e, and as we get such type of curves, the flow keeps on increasing in this particular way. Now, this continues till we obtain choked flow conditions here. It keeps on, when we keep on reducing the pressure and we find that the flow rate keeps on increasing. Okay. So, this goes on till the pressure here is under choked flow. Choked flow means we denote the properties by means of asterisks. So, therefore, this continues till we get P star by P 0. Okay. This I will make with a different line. So, this is till this portion we get the maximum flow rate in this particular case, and this occurs for M a equals to 1 and this particular point is P star by P 0. Okay. Now, after this what happens is, after this we again keep on reducing the pressure. Now, when we again keep on reducing the pressure, what happens is we find that P cannot be reduced any further, okay, that becomes constant. P b can be reduced, but P b is not equal to P e, P cannot be reduced any further. Since P cannot be reduced any further, the flow rate cannot be increased any further, the flow rate becomes constant after this. This is what we find when P b is less than P e. This is this particular condition. We find that we cannot reduce the flow rate any further. Okay. And but here what happens is, when we are keep on reducing it, the flow is coming. Then after here what happens, the compressible fluid, it expands isentropically in order to match this reduction in pressure. Is it clear to you? What happens once choked flow condition is arrived, or choked flow means P e equals to P b equals to P star. Okay. Till that portion we can P e is equal to P b and your flow keeps on increasing. Okay. Moment P b becomes equal to P star, after that if we reduce the flow rate further, then what happens, P e cannot respond anymore. And as a result the flow rate becomes constant, the flow rate cannot be increased any further by reducing the back pressure or the exit pressure. Then in that case what the flow does, the flow then what it does, it comes here, and then in order to compensate for this mismatch in pressure, it expands isentropically from pressure P star to P b. Do you understand? And this is in the form of free dimensional waves. We cannot approximate it by one dimensional flow theory. Is this portion clear to all of you? Okay. So, therefore, if we reduce the pressure below this, then we find that here under this particular condition we have sort of a pressure waves or shock waves. Yeah, these are known as the shock waves. Okay. Shock waves generate and we cannot reduce the pressure any, or rather we cannot reduce the pressure any further, and here also the flow rate it becomes constant. So, therefore, we find that the pressure distribution here at G equals to G max when P e becomes equal to P star. Further reduction is not going to affect the flow any further, even though PB can be reduced, but it does not give anything. It does not what happens is the flow which leaves the nozzle here, it has to expand to match the lower back pressure. And in order to match, we find that this expansion which occurs, that is 3 dimensional in nature, and the pressure distribution under this condition cannot be predicted by 1 dimensional theory. As a result, we cannot predict the pressure, we cannot plot it properly here. It cannot be done by 1 dimensional theory. Is this part clear to all of you? Well, so therefore, remember one thing, that for this particular case, then what do we get? For this particular case, therefore, we had seen that what will be the flow rate under this condition. We had got the expression for Mach number equals to W by A for maximum conditions. Where did I keep the slide? Yeah. So, we find that for the maximum conditions, we can get it for Mach number equal to 1, is not it? And I do not see if I had kept the final slide where I had deduced this particular condition. du dw, just a minute, this is the case. Yeah. So, what did we find? We find that W by A was given by this particular expression, okay? And if we put M A equals to 1 here, then we are going to get the maximum flow rate, and that occurs under choked flow condition where A equals to A star. Do you get my point? So, therefore, what do we get is, I will write down W by A once more. This is root gamma this is what that we had obtained. Now, W by A star, that is nothing but equal to root gamma by R P 0 by root T 0 1 by gamma plus 1 by 2 gamma plus 1 by 2 into gamma minus 1, is not it? So, if we divide this by this, what do we get? We get A by A star, is not it? What is A by A star then? We can write it down as 1 by M A plus 1 into 1 plus gamma minus 1 by 2 M A square. Please perform these derivations, otherwise it is going to be here. I am just deriving it and you are just copying it down, that is not going to help you much. Okay. Please derive these derivations and then do them accordingly. So, therefore, we find that A by A star, that means area divided by the choked flow conditions, this can be obtained from an expression. Again we find that A by A star is function of Mach number only. Gamma is a constant, diatomic gas is 1.4 and etc., we know it. Okay. So, therefore, A by A star is again a function of Mach number, correct. So, therefore, since it is a function only of Mach number, we can plot or we can represent graphically the variation of A by A star with Mach number. Yes. So, if we do it, if we plot A by A star as a function of Mach number, what do we get? We get something of, we get a graph or a curve something of this sort, okay, where this is obtained as MA equals to 1.0. So, therefore, what do we find from here? We find that for every Mach number there is a unique A by A star. Listen to what I am telling very carefully. For every Mach number, if you take up any particular Mach number, you find a unique value of A by A star, okay? And this is very much evident from this particular equation also. One Mach number you get a unique A by A star, agreed? But if you take for any A by A star corresponding to any A by A star, we get two values of Mach number. One is for less than 1 and one is for greater than 1, taking into account the existence of subsonic nozzles and supersonic nozzles. Okay. So, therefore, please remember that for any A by A star except your A by A star equals to 1.0, there are two possible values of MA. So, this shows supersonic nozzle is diverging. So, this is clear to you. So, therefore, we find, so from here we find that why your A by A star is so very important, and we find that for any particular Mach number there are two possible, for any particular Mach number there is one unique value of A by A star, but for any A by A star there can be two values of Mach number except for the condition of Mach number equal to 1. So, therefore, we conclude here, and in the next class we will just be referring to the denominators which we had obtained for your compressible flows and to homogeneous flow, and then we will try to derive certain things from it. Okay. Thank you very much.